Hey, all, this is Tyler. As I've been learning Zig and systems programming, I've learned a few things and wanted to start making some videos to start share them around, particularly for people who want to learn Zig or Rust or any other systems programming language, C, who come from an uninitiated background like myself. And so this could be the first video in a series of videos. I hope to help explain and demystify things, particularly for those who are learning Zig. We're going to take a pretty big Zig focus in this series, but a lot of the information I hope can be helpful for those who are learning other languages such as Rust or C. So first thing that I think is really confusing for people when they get into Zig is dealing with allocators. In Zig, you have to always pick an allocator if you want to allocate data on the heap. And don't worry, we're going to get into that. If this is for the uninitiated, I'll get into that. But if you want to use data on the heap, you need to use an allocator. And the thing is, Zig comes with a lot of allocators in the standard library. You have the general purpose allocator, you've got the page allocator, you've got the arena allocator, and you've got a few others. And that can be a bit overwhelming to people who've never used any kind of manual memory management and never have had to call malloc or free or anything like that. So the hope is that with this video, we can get down to some basics of what it means to manage memory, why it's important, and how allocators fit into that. So we're going to go through this. We're going to start by looking at what memory a process has access to. So this is what I've got in this little chart drawn out here on Excalidraw, and I want to highlight some things. So in a process, first, a process is just an abstraction for the kernel or the operating system. And as a side note, everything I'm talking about here is mostly specifically to Unix platforms, though there might be some carryover to Windows. I'm not a Windows expert, but a lot of this information could possibly carry over to Windows, but it's specific about Unix. Okay, so a process is just an abstraction for the OS to describe a program that is running and the resources that are allocated for that program, such as, processes have resources like, you got file descriptors. File descriptors are used to open and close and read files, or rather they're used to read and write files, I should say. You get a file descriptor when you open a file. You also get memory when you have a process. And this resource is super important. It belongs obviously to the computer. And whenever you have a process that needs to have memory, all processes need some memory to run. You have to get that from the kernel. And so the kernel keeps track of this data. In this section here, we're going to say this, if we have all this section as memory allocated for a process, there's lots of tiny different sections in there. So up here we have what's called kernel memory. Make that E better. Kernel memory. Okay, and this is stuff that our process doesn't have access to. It's just metadata. Going to be metadata. And this metadata keeps track of, what file descriptors you have, helps keep track of other data structures used to keep track of the process. After that, you get into what's called user memory. So all of this is user area memory. And what you'll have here at the top, you're going to get things like your args. So any command line arguments will go in here, as well as your environment variables. You'll get that. And then following that, you get your stack. You need a section of memory dedicated to the stack. And these are for building up the stack frames of a function. So when a function is called, it has to allocate some memory for the processing of, parameters, any variables that are used, local variables that are created, and possibly the return value. Those need to be created on the stack so that you can do some calculations. And it's called a stack because once the function returns, there's a thing called the stack pointer, which points to the top of your stack, and it will decrement back up to the previous function call. And that memory that you're using before can be overwritten, rewritten. So it's a first, pop on, pop off kind of system, hence a stack. Okay. Between the stack, you get this kind of area. We're going to say it's uninitialized data, uninitialized memory, and you can have your heap. So what's the heap for? Heap is for the stack, let me write this. The stack is for your local variables. Wow. Local vars. Your heap is going to be for your dynamic variables. That might sound like I don't know, a duplication of terms, right? It's dynamic and it's variable. What do you mean? Well, things that might grow. So say a list. For example, in Python, a list can grow, and you can add more items to it. You don't have to dedicate and say this list is going to be 100 items long. You can say it's runtime known. We don't know how long this list is going to be, but I need it to be as long as it needs to be. And that kind of information is not stuff that can be put on the stack. The stack has to be known what size of data we're going to put. The stack needs to know so that when it builds the stack or stack frame for a function, it can allocate enough memory. And if that memory is not known until runtime, or in the middle of the running of the stack, it can't allocate that memory. So the heap is there for that. Below the heap, you're going to have stuff. This is more stuff like you can have some section for perhaps global, static data, and you can have room for your text, which is the text section. It's just the section that contains the code, right? So the code you're actually running has to be in memory as well. And then we notice that I've left out these areas here. So in this area, you got room for your stack to grow that way, and you have room for your heap to grow that way. And so there is limited space for the stack. That's why you often get stack overflows, or not often, but you can get stack overflows if you write, for example, a recursive function without an escape, right? If that function continues to recurse, it'll eventually overflow its space, and that causes stack overflow. Same with the heap. The heap grows up. But I do want to emphasize that this is all an abstraction. This is all virtual memory. And it's not that the memory doesn't exist for real. All this stuff is on physical RAM. It's just that they're not actually contiguous, right? So when we say the stack grows down and could overrun itself, what we're really saying is that the process is going to be limited by the OS to a certain amount of memory, maybe 2 gigabytes or something like that. And if that limit is breached, if it becomes too much, then it's going to overflow. But that the stack actually overflows itself into the heap isn't something that actually happens. These are all just different parts of your memory. Now, when we talk about allocators, there's actually only one area that we're really interested in, which is dynamic variables. Everything else is handled for. So kernel memory, we don't have to worry about that. Kernel memory is handled by the kernel. Same with the args and env. The kernel just sets that up. It knows what your environment should be. It knows what your argument should be. It gets that from either your shell or however you're calling this program, and it sets it up. The stack is set up, and it's going to be managed Like you're going to get an area of the stack, and that's going to either be managed by the way the programming language works or the kernel itself. Once again, same with text and same with the global and static area. The only area that we as programmers need to manage is the heap, because the program, the OS can't understand it, or rather doesn't know what we need. And the program itself, or maybe not the program itself isn't the right word for it, the language itself doesn't know. It's something that we have to manually code into the program. So when we talk about allocators, manual memory management, we're talking about what goes on in the heap. So let me write that right there. Point of allocators. Okay, that takes us to the end of what I wanted to talk about for basic manual memory management, or understanding the purpose of what we're talking about when we talk about memory management and allocators. Next video, I hope to talk maybe more in depth in how allocators are used. Maybe we'll run through some examples. I haven't thought about it yet. But particularly, I'd like to start getting into some internals with Zig allocators, maybe not too depth of Zig allocators, but into understanding the reasons for having multiple allocators and why Zig focuses so much on allowing us, or not just allowing, but kind of forcing us to choose allocators all the time. And once that's done, once we have a good idea of the different kind of allocators, the hope is that then you'll be able to understand which allocator you should use in general and in specific cases. So that is that. If you have questions, you can leave them in the comments. I'll leave a link to my Discord channel as well. You can find me there. We can, I'd love to hear any more questions, any more follow-up that needs to happen. Just let me know. Thanks. Bye.